everyone. We have completed this analysis tool so far, like stability, controllability, observability, all that. Now, the question is, can we make use of some of those designs and some of those tools for control design. So, it is also called as control synthesis actually. So, analysis part being over, we will continue with the synthesis part next couple of classes. So, first one in the series we will see this pole placement control design in this lecture 21. So, let us start with the concept. We are given a kind of plant for which the dynamics are known to us, and it is a linear system of course, x dot equal to x plus b u, and then can we design a control system u. I mean that is what we are interested to ask in this question, I mean in this lecture. So, what the assumptions behind this particular design? First thing is the system is completely state controllable. Okay. So, I mean if it is not controllable, obviously you can't do anything, and hence we cannot do pole placement design either. And the second one is the state variables are measurable and are available for feedback. So, in other words, you can actually implement this control. So, if you design a formula for u in terms of x, then x should be available for computing u. I mean that is the, if part of the x is not available, then you can have your mathematics ready, but you cannot implement the controller because information is not available otherwise. Okay. We also assume that the control input is unconstrained. That means normally the control inputs are typically constrained. That means the magnitude of control and the rate of control, all that are not really infinite. They have to be constrained by physical constraints, they have to be constrained by like energy input, all sort of things. But here we will assume, as far as the theory development is concerned, that the control input is unconstrained. So, these are the primarily three assumptions that we will rely on actually. First is system is controllable, second is states are available for computing the controller, and the third is the control is unconstrained actually. Okay. So, let us see what is the philosophy here. Okay. The objective here is the original system that we are talking, right, that is x dot equal to x plus b u. Okay. Original system what we are talking here is something like x dot equal to a x plus b u. Okay. Remember this the system is controllable, but it is by no means it is need not be stable, what I mean. So, the system can be unstable, or even if the system is stable, the poles of the A matrix, that means the eigenvalues of the A matrix, okay, need not be at the desired location. Okay. That means even if you ignore this control input for a second, then even if the system is stable, okay, you may not the system may not be performing the way we want it to perform actually. So, we want to enhance the response, sometimes we want to increase damping sometimes, like that actually. Okay. So, just because the system is stable doesn't necessarily mean that we do not need a control system design, we may still need that actually. Okay. So, that is what you are telling. So, what you are telling here, I mean unlike our classical control system, typically in classical control system we will be bothered about dominant poles. That means in PID design we will worry about only two dominant poles and try to locate them. But here we are telling no, we need not worry about only two, but we can talk about all the pole locations. Okay. Okay, all the pole locations. Okay. Should lie at our choice. The locations should be dictated by our choice, which will eventually come from either time domain specifications most of the time, or sometimes partly from frequency domain specification also. So, this mu1 to mu_n are the desired location, remember that. So, in other words, the original system poles need not be at those locations, it can be somewhere else. Okay. But we want to design a controller in such that the closed loop system pole should be located here. Okay. So, as I told, the difference from classical approach is not only the dominant poles, but all poles are forced to lie at specified desired location. That is the difference actually. Okay. I already told necessary and sufficient condition turns out to be the system needs to be state controllable, completely controllable, what I mean. Okay. All right. So, by assumption this is controllable anyway, so we satisfy this actually. Now, philosophy of okay, what is the idea there? What is the philosophy of pole placement control design? We have a plant which is x dot equal to x plus b u, linear system dynamics, and we want to design a control vector u in the state feedback form, that means u equal to minus k x actually. Okay. So, if you design that u equal to minus k x, okay, and then the closed loop system dynamics becomes x dot equal to a minus b k into x, okay, and we typically tell that okay, this is nothing but the closed loop system matrix a minus b k. So, we have an idea that suppose somebody kind of gives us this k, then this is our closed loop system matrix. Okay. But the problem here is the reverse, we want to design a k. The formula is given to us u equal to minus k, that is the formula we want to kind of use for the control design. So, the freedom of control is actually boils down to freedom of designing this k matrix. Okay. So, the gain matrix needs to be designed actually. Okay. So, anyway, so after designing that, the closed loop matrix becomes a minus b k. Okay. And the philosophy is like we want to design this gain matrix k in such a way that the closed loop poles or the closed loop characteristic polynomial rather, okay, is dictated, which is dictated by the SI minus of closed loop A matrix, determinant of that. Okay. So, left hand side is closed loop characteristic polynomial is nothing but the desired characteristic polynomial, because the pole locations are known to us. So, it is this right side is nothing but the desired characteristic polynomial. So, if these two becomes equal, then obviously the closed loop system matrix will have these poles actually, that is the whole idea. So, okay. So, once again this mu1 to mu1 is known to us. So, obviously once the desired poles are known to us, the desired characteristic polynomial is known to us, and hence all that we are doing is the closed loop system matrix, which is a minus b k, and the characteristic polynomial is given by that S I minus this a minus b k determinant. So, we are just making them equal to actually. Once we make it equal to, then obviously our job is done actually. The question is how do you make it equal? There are various ways of doing that. We will study method 1, 2, 3 here. And method 1 is first, but before we go there, before we develop further things, first we will study single input system. Okay, pole placement design has unique solution if you consider single input system. States can be many, but the control is just single. In that situation, pole placement technique design is unique, and it I mean there is no confusion for that actually. So, let us study about that particular thing. And remember, when u is scalar, then b is a vector, it is no more a matrix actually. Okay. So, okay, method 1, that is what we talk about. So, for the very first step of any control design, not necessarily pole placement, is check controllability. Okay. I mean once the controllability condition is satisfied, then there is hope that you can actually design a controller, otherwise no actually. Okay. So, first thing we need to do for any control design, even if it is not told to us explicitly, is to check controllability. Okay. Now, we are telling method 1 is very straightforward, just derived from this condition that we just discussed here. So, this particular method is not very neatly kind of suitable for higher order systems. It is easy to follow for low order systems in general. So, if n is less than equal to 3, then probably you can do it manually. This is like a manual method basically. So, what you are telling this, we have a single input system. Okay. That means okay, you have this x dot equal to a x plus b u, okay, and u is scalar, and u you are telling minus k x. So, x dot equal to a minus b k times x, that is what we are interested here actually. That means the dimension of this a minus b k, okay, what you are telling here, well, let me, okay, a minus b k, okay. So, that is the dimension has to be n by n actually. Okay. And remember, b dimension is nothing but n by 1. Okay. So, k dimension has to be 1 by n actually. Okay. So, k has to be of dimension 1 by n. Okay. So, that is what we are telling here, that we select a matrix of let us say it is n equal to 3 here, that is what we are talking. So, we select a gain matrix k 1, k 2, k 3, 1 by 3 here. Okay. It is just a row vector actually. And then we substitute that in the formula that we just talked about. This is the left hand side of characteristic polynomial, that is what you substitute here. So, S I minus a plus b k determinant, that should be equal to mu 1 s minus mu 1 into s minus mu 2 into s minus mu 3 really. I mean you do not have to continue up to n, you have 3 poles only. So, in principle this is if it is a third order system, then this has to be 3 basically. Okay. S minus mu 1 into S minus mu 2 and S minus mu 3. So, you have a third order polynomial in the left hand side and you have a third order polynomial in the right hand side. So, just equate the coefficients and solve for k 1, k 2, k 3. So, a third order polynomial will give 3 coefficients and this well 4 coefficients in general, but S cube plus that I mean 0th order term taken into account. You just take this first order coefficient is S cube, which is which does not give us anything, it is just an identity. But afterwards S square will have a coefficient, S will have a coefficient, and we have a constant term that is also a I mean the kind of a coefficient for 0th power of S. So, if you equate these two from the I mean these 3 coefficients, you will get 3 equations, and our entire equation had freedom of 3 k 1, k 2, k 3. So, we can actually solve this. Okay. So, easy I mean I am not giving an example here, but rather fairly easy to do that. All that you are doing here is just equating the coefficients and solving for k 1, k 2, k 3. Once you solve for k 1, k 2, k 3, your gain matrix is ready and hence your control formula is also ready, u equal to minus k x. Okay, that is how it is. Now, method 2. So, why okay, method 1 is in general it is okay for n equal to 1, 2, 3, okay. But if it is more than 3, 4, 5 and all that, it becomes very cumbersome to do that manually, and even if you are able to write the coefficient equations manually, then probably you need to do symbolic computation anyway for solving this in a computer manner or maybe numerical methods, things like that. So, this is not a very neat way to design pole placement controller for higher order system. So, obviously people have thought about how to circumvent that by various other alternative approaches actually. So, let us study that method 2, which is little more general actually. Okay. So, what you are having here is x dot equal to x plus b u. In general, this is not third order system, it can be any order system, but u is still a scalar. Okay. So, we have u equal to minus k x and k is nothing but a row vector 1 by n row vector actually. Okay. All right. So, once you have that, then obviously a is that and b is that. Okay. What we are assuming here is the system is in first companion form or controllable canonical form. That is the first I mean we will also see if it is not in this form what to do later, but let us assume that the system is in controllable canonical or first companion form, for which the A matrix is given like that. We have studied that before. All that n minus 1 rows will have this particular structure, B will have all 0 0 zeros, last entry is 1 and the last column last row here is some numbers actually. That is the first companion form. Once you have that, then and the k is that way. So, what you have x dot equal to a minus b k into x or ACL x, where ACL can be computed that way. Remember b times k, when you put k, okay, b is this and then k you put it here, okay, b times k you multiply k 1, k 2 up to k n, this is a row vector. So, this one has n by 1 and this is 1 by n. So, it will result in n by n matrix actually. Okay. So, what you I mean is rather easy to see that this is like if you multiply first I mean first 0 to k 1 is 0, 0 to k 2 is 0, everything else will be 0. So, the first n minus 1 rows will be typically 0 and the last row will have some numbers which is nothing but minus k 1 minus k 2 and all that minus b k term will have result that. So, that is what is this is A matrix minus b times k is nothing but simply that actually. First entries are all 0 and then the last entries are k 1, k 2 up to k n actually. Okay. And the neat part is because these are all 0, these first columns are I mean first n minus 1 rows are not disturbed at all actually, they are just remaining as it is actually. So, we will have a minus c I mean that a minus b k or ACL which is like this is also in the first companion form. Okay, that is 0 1 0 0 all sort of things, first n minus 1 rows will not be perturbed and then only the last row will be disturbed actually. Okay. So, that is what we will get here. Now, if you have the closed loop pole locations known to us, okay, and that is s minus mu 1 or multiply by s minus mu 2 all that up to s minus mu n, then it will result in a characteristic polynomial and this characteristic polynomial will lead to a closed loop system matrix in this form. Okay. Suppose you take any output by input sort of thing, if you want to convert it to state space form, then this will be the resulting A matrix in the controllable canonical form. and that primarily comes from this characteristic polynomial being this way. Okay. So, what you have here, instead of equating the characteristic polynomial coefficient by coefficient, we are formulating a system closed loop system matrix, okay, and then we are we are equating the matrix as such actually. This is the matrix for the closed loop system matrix, and that is the closed loop system matrix which will result from closed loop system poles actually. Okay. So, by equating the element by element matrix form, the task become much simpler, because you do not have polynomial expressions to equate, you are just simple expressions to equate in the last row only. So, because the first n minus 1 rows are identically same. So, they are just identities actually. Okay. Only equations are formed only from the last row of this matrix and last row of that matrix. So, you will just element by element will equate, and then that will result in this for example, this first one minus alpha n minus k 1 will result, that is equal to minus alpha n. Similarly, the second element minus a minus 1 minus k 2 is nothing but minus alpha n minus 1, like that. Okay. So, then you result this set of equations will pop up, and from which we will be able to compute k 1 to k n very easily rather. So, in a vectorial notation, k is nothing but alpha minus a, where alpha is a row vector containing alpha 1 to alpha n, and then a is a row vector containing a 1 to a n actually, alright. So, but remember it is a reverse order actually, order is reverse. So, this you have to be slightly careful while using this actually. Okay. See what you are getting here is k 1 is equal to alpha n minus a n, and k 2 is alpha n minus 1 minus a minus 1, whereas k n is nothing but alpha 1 minus a 1. So, it is kind of a reverse order. So, this vector alpha and n is to be defined properly actually. So, do not just start defining alpha 1 to alpha n, rather it is alpha n first and then alpha n minus 1, then alpha 1 at the end. Similarly, a vector is also defined that way. Okay. Now, but after you remember that is very easy, because you have this coefficients ready anyway, right. So, it is just a formula actually. So, what is the design procedure then? Okay. Design procedure is like, let us say alpha, okay, these are the closed loop pole locations. So, we just expand and collect these alpha 1, alpha 2 up to alpha n, that is where you will collect. And then we already have this this matrix, this what is that, this coefficients a n minus 1, all that already known to us from the system matrix actually. Okay. So, then just use the formula and get the answer sort of thing actually. This is just whatever these gain coefficients are given like that, and you are done. The design is u equal to minus k x anyway. Okay. Now, the question is, what if it is not in the first companion form? See, these are all valid. Okay, this system matrix nicely popped up because it is a first companion form, that is also first companion form. So, we are kind of lucky to get all that actually. Okay. Now, the question is, obviously life is not in first companion form. So, what you do in general basically? Then what you, then people have thought about, that is probably one of the great contributions. What people thought about it, instead of starting directly, which will lead me to complicated expressions and all that, is there a transformation which will take me to first companion form? Okay. So, starting from any general form, can I take it to first companion form actually? Okay. So, that is what the idea here is. So, let us define a transformation x equal to t times x hat. Obviously, t has to have it is a full rank matrix, otherwise the inverse will not exist actually. Okay. So, t needs to be full rank, this is a transformation. So, that means if I know x hat, I can get x, if I know x, I can also get x hat that way. Okay. So, then we want to kind of visualize the problem in terms of x hat variable, let us say. Okay. So, x hat is that way, x hat is nothing but t inverse x. So, x hat dot is also t inverse x dot, right. So, this is this expression gives like x hat is nothing but t inverse x, and t is a constant matrix. So, this will give us this x hat dot is equal to t inverse x dot actually. Okay. Okay. So, then this x dot is nothing but x plus bu, that we know, and again we want to convert x. So, x is nothing but t x hat actually. So, what expression you are getting is like t inverse a t times x hat plus t inverse b u. That is very similar to what you get in similarity transformation really. Okay, similarity transformation for a matrix. is given by P inverse A P, and P is nothing but eigenvector, I mean the matrix consisting of eigenvectors and all that. Here it need not be eigenvector, it can be, I mean there will be some other matrix T, okay, but it is T inverse A T, okay, that is like kind of I mean similarity transformation basically. Okay. So, what is that? I mean the philosophy here is design a T or the transformation. So, you have to pick up a T such that, okay, this T inverse A T now will have first companion form. So, if this is first companion form, then we are ready to start our problem basically. Because earlier we started with the assumption that this is in first companion form. Now, we are interested in transforming the system into x-hat variable. So, that in x-hat coordinate system, okay, the matrix system matrix is in fact in first companion form. The question is, can we do that? Is it possible to do that? And that is, I mean the great thing is it is certainly possible, and T takes this form actually M into W, where M is nothing but controllability matrix, okay, and W is something given like that, which is nothing but coefficients of the open loop characteristic polynomial. I mean that is what the A matrix coefficients basically. Initially you have A matrix coefficients which are nothing but coefficients of this characteristic polynomial if it is in the kind of first companion form. In general, otherwise it will have this A1, A2, all these AN will come from the open loop A matrix actually. We will see an example to see how do we select this and all that actually. Okay. So, open loop characteristic polynomial will give us these coefficients, and this M, I mean is nothing but the controllability matrix. So, you have the T is nothing but M times W, and once you apply this, then you are done actually, the T inverse A T will be ready now. So, this will be in first companion form, and hence you can compute your gain matrix in terms of x-hat variable, remember that. So, U will be in terms of x-hat, but x-hat and x you can again use that, x-hat equal to that, and then you can write it in terms of x actually. So, that is not a problem. So, that is what I am written here, U equal to minus k hat x hat, okay, but k x hat is nothing but T inverse x. So, k what ultimately you are interested in k. So, this k is nothing but k hat, okay, times T inverse, yeah, that is your gain matrix actually. Okay. So, just a comment here, because of this role in control design, I mean you can very clearly see that there is a need for controllability matrix and things like that. Okay. The first companion form is also known as controllable canonical form. I mean this is just a comment sort of thing actually. Okay. First companion form is heavily used in control design really. Okay. So, that is why the term comes from there actually. Okay. So, what is the pole placement design steps in general? This method 2 is also called as Bus-Grove approach for their contribution really. Okay. So, first thing to do is controllability condition check, you have to check controllability condition, then you can form the characteristic polynomial of the open loop A matrix. So, Si minus A characteristic polynomial is nth order polynomial. So, this is given in this form. So, you can collect this A1, A2 up to An, which will be necessary for forming this W matrix, that is where these coefficients will come from actually. Okay. So, you can collect these coefficients, and then the transformation matrix is ready, T is nothing but M times W, where M is controllability and then W is also ready now. Okay. Now, we can write the desired characteristic polynomial, okay, which is in this form, okay, and then this will give us a method of selecting this alpha 1 to alpha n now. Okay. These are the coefficients of the desired characteristic polynomial. Okay. So, A1 to An are ready from open loop characteristic polynomial, alpha 1 to alpha n are ready from desired characteristic polynomial. Okay. And the desired gain matrix is nothing but this one, right, k hat times T inverse, and k is nothing but that what we discussed before this time, this will be k hats now basically. Okay. So, once you substitute all that, then this is nothing but that actually. So, you have a gain matrix which is ready for you actually now. Okay. So, u will be ultimately minus k times x, okay. After multiplying with T inverse, this k will act with x actually. So, that is the method 2 approach. So, method 1 is just equating the coefficients of the two polynomials, these two polynomials, whatever one polynomial is here, one more polynomial here, you are directly assuming a gain matrix form k1, k2, k3, and then if this characteristic polynomial will be for the closed loop will contain k1, k2 up to kn all that, and then equate the coefficients, solve for those equations. Method 2 is little more systematic and hence simpler, and then this procedure, once you follow this procedure, the gain matrix will naturally pop up actually. Okay. Now, there is a method 3, okay, which is personally I like the most actually, because it is a direct formula, that is my personal preference probably. Okay, so, this is called as Ackermann's formula. It is in fact it will lead to a formula ultimately. So, let us try to understand that. So, we instead of ACL for notational simplicity, we will just write it as A tilde here. I mean both are same anyway. Okay. So, the closed loop A matrix A tilde is nothing but A minus B k, and the desired characteristic equation is like that. This is already we know actually. Okay. So, this suppose you want to expand that and all. Okay. So, the characteristic equation will turn out to be like that. So, this part is polynomial. If you equate it to 0, it is characteristic equations. Okay. Now, this characteristic equation we will call it as phi of A tilde. Okay. I mean phi not A tilde really, but it is like phi of S sort of thing, okay, because it is a scalar equation. Now, there is a great theorem in matrix theory, which is Cayley-Hamilton theorem. Probably you might not have seen its usage so extensively, but here is a direct usage actually. So, what it tells this Cayley-Hamilton theorem is that every matrix will satisfy its own characteristic equation in matrix equation sense basically. So, characteristic equation is typically a scalar equation, okay. But once you apply Cayley-Hamilton theorem, the scalar expression that you have, if it is coming from some matrix A, then the same matrix will also satisfy its own characteristic equation, which is a very great theorem actually. Okay, because you have information about only a one equation, one scalar equation information, and you are able to conclude a matrix equation directly from there, which is n by n matrix equation. That is the beauty actually. Okay. So, if you see this usage of Cayley-Hamilton theorem, let us say we want to apply. This is nothing but the characteristic equation for the closed loop matrix A tilde. Okay. So, obviously, this A tilde will satisfy a matrix equation that way. So, if you just see this equation as whatever s to the power n plus alpha 1 s to the power n minus 1 all that, okay, and the exactly similar equation you can write it here. Okay. Probably there is a small print mistake basically probably. So, alpha n times I basically. Okay. So, you cannot write a scalar equation there actually. Okay. So, alpha n times I will happen there actually here. Okay. That is equal to 0 anyway. So, without complicating the matter, we can just take n equal to 3 for understanding the concept, and it will be valid for n equal to 4, 5 any order basically by the way. So, without loss of generality, we will consider n equal to 3 here, and we will also let us before applying this Cayley-Hamilton theorem and proceeding further, we also note that these powers of A tilde will be necessary for us. Okay. So, we will also see that I equal to I, that is identity anyway, but A tilde is nothing but A minus B k, and A tilde square is A minus B k into A minus B k. So, if you expand, then that will turn out to be like that. So, partly I am not expanding everything. I mean what you are telling, we are expanding only the terms that are necessary and leaving out with A tilde expressions, that is all right with us actually. We do not have to write all this in terms of A, B and all that. Similarly, A tilde cube will be A tilde square into A tilde. So, A tilde square already we have, okay, into A tilde is A minus B k. So, we expand whatever we have and then leave out the polynomials in terms of A tilde for simplicity actually. Okay. So, A tilde is that, A tilde square is that, and A tilde cube is that. Okay. So, what you observe here nicely, see A tilde one A matrix pops up with some other matrices, A tilde square one A square matrix pops up with some other polynomial, okay. A tilde cube, A cube pops up with some other things actually. That is the fact that is going to be used later actually. Okay. Now, the Cayley-Hamilton theorem will excite and tell, okay, this is nothing but this phi of A is A tilde is 0. Okay. Remember, this is valid for phi of A tilde, not for A, because A tilde is the closed loop characteristic polynomial, I mean closed loop system matrix, and this is what we want A tilde to satisfy, the characteristic polynomial. Ultimately, we want it to satisfy this equation, that is why we started with. So, the closed loop A tilde matrix will satisfy this equation, not phi of A. Okay. So, that is what we tell here. So, we want to formulate this phi of A tilde first. So, phi of A tilde for n equal to 3, we have only 3 terms actually, right, 3 terms from that side, remember that, not from that side, but the 3 terms from that side, right hand side. So, the 3 terms from right hand side are like that, okay, alpha 3 into I plus alpha 2 A tilde plus I mean alpha 1 A tilde square plus A tilde cube, and all these expressions we have just derived. Okay. So, we substitute all that whatever expressions we had, and it I mean we can collect the first coefficients, where first coefficient is from here and first coefficient from here, first coefficient from here, like that. Okay. And it turns out that this particular thing that you are talking about, looking at, okay, this particular thing that you are looking at, okay, is nothing but phi of A matrix. Okay. Right. Then we have a bunch of other things actually. Okay. So, that is what we want to excite, and then tell, okay, if the phi of A tilde is nothing but 0, okay, but phi of A what we have here is certainly not equal to 0, phi of A is not equal to 0. Okay. So, let us use this property and tell, okay, what we have ultimately this equation tells us that phi of A tilde is nothing but phi of A minus all these actually whatever terms we have. Okay. So, but what we know is this is 0, okay, because that is Cauchy-Hamilton theorem, phi of A tilde is 0. So, what are left out actually, you can actually get an expression solution for phi of A basically. Okay. So, phi of A is nothing but all that, and in a partition matrix sense I can write it that way, where the beauty is it is again this controllability matrix is popping up very neatly actually. Okay. So, what you are having here ultimately is if I want to write it, so the system is kind of completely controllable, we understand. So, this matrix, this controllability matrix is non-singular, and hence this is okay, well I think there is a small print mistake again here, times phi of A here. Okay, I will write that actually. Okay. So, here it should be okay, here this phi of A will multiply. Okay. Okay. So, if I take I just want to solve it for this particular matrix or kind of whatever I see here is a matrix, right. So, this matrix into this matrix is nothing but phi of A. So, we want to solve for this matrix, and this matrix is nothing but this inverse times phi of A. I pre-multiply both sides with this inverse actually. Okay. So, what I am getting here? I am getting, so this particular matrix, okay, consists of several rows and all that, but what I am interested in, I am certainly not interested in first 2 rows actually, I am interested in only the last row, that is my gain matrix actually. So, if I want to extract my last row, then what I do is I simply pre-multiply by 0 0 1 actually. If I multiply 0 0 1, it will give me the last row basically. So, my ultimately what you see here, k gain is nothing but a formula, directly it is a formula actually. So, 0 0 0 I mean 0 0 1 with the controllability matrix inverse times phi of A. So, that is the formula that you are talking about, recurrence formula actually. So, in general, okay, if it is of n states, like n number of rows, I mean n number of states, then you have to have a little general formula for this, which will tell us that this is 0 0 0 all the way up to n minus 1, then last one is 0, then you have a controllability matrix inverse, then phi of A actually. Okay. Where phi of A is nothing but the same expression as phi of A tilde, where A tilde substituted by A basically. We started with phi of A tilde, right, Cauchy-Hamilton theorem. Okay. Okay. We started with all that actually, phi of A tilde. So, this is like that actually. Okay. All right. So, this is the method 1 2 3 that we discussed actually. So, method 1 is just equating the coefficients, method 2 is a Bhaskara formula, we have actually steps to follow, and method is just direct, we just have one single formula for designing the K matrix actually. Okay. So, let us talk about little more things. So, this all this method 1 2 3 that we discussed, it only gives us mathematical formulas provided we know the closed loop poles. Nobody has told us how to design closed loop poles and all that, and nobody will ever tell us either, these are all problem dependent anyway. But there are guidelines available, and the first guideline tells us that do not choose the closed loop poles far away from the open loop poles, and change only those poles to a different location whenever it is badly necessary, otherwise do not actually, because changing the pole location is not free, we can change the pole locations only by using control. So, that means the difference of this open loop and closed loop pole locations is done by control effort actually. So, the moment you change these poles different, I mean far away to each other, then the control demand suits up actually, control effort suits up actually. Okay. The second is do not choose the closed loop poles very negative. That means you are telling, okay, if the negative side is stabilizing, so I will go negative far away from the negative half actually in this plane. But that is also not good, because you remember, if you have a negative negative pole location, then there is exponential e to the power minus sigma t term actually. Sigma is the real part of the pole location actually. Okay. So, if the sigma is large, then that term is very large, that means it excites fast decay and things like that. Okay. That means in frequency frequency domain, it leads to large bandwidth sort of thing. The response becomes very fast. That means for a little input, it will system will try to respond very fast. So, that means if you see it in a negative point perspective, then it tells us, okay, what about noise input? Noise is also an input. It is a low magnitude high frequency input, but even if it is a low magnitude, the system reacts to every little thing. So, that means it will also try to react to noise actually. So, the noise amplification property becomes predominant if once you have this far away poles being there. So, unnecessarily do not get too much kind of ambitious to put the closed loop poles far away from the imaginary axis actually, that is not good either. So, looking at a little more in depth, suppose the open loop pole, one of the pole is located far away in the left hand side, probably we would like to bring it back closer to the imaginary axis. Some applications are like that. So, just because it is far away from the imaginary axis in the left hand side does not mean the system properties are really good actually. It may be less robust to the noise actually. Okay. So, to increase robustness and all, we can aim for bringing the pole locations little more closer to the imaginary axis. Okay. All right. So, these are just guidelines, and there is another guideline. Okay, how do we select if you are kind of confused, how do you select, how do you place the pole locations in a good way actually. And one suggestion is you can use Butterworth polynomial, which is given some form like this, S by omega 0, where omega 0 is like natural frequency, some design parameter constant. So, you select some omega 0, and then S by omega 0, that is a closed loop pole locations, you kind of attempt to distribute this formula, where minus 1 we can use De Moivre's formula sort of thing, where you can write expand in terms of complex exponential actually. Okay. So, this complex exponential, okay, and n is nothing but system order basically, and this will churn out a bunch of poles, okay, because k is 0, 1, 2, 3, it is an infinite series anyway basically. So, you have to select only n of them, because that is what we are interested in, and obviously we are not a fool to select unstable poles. So, we will certainly select only poles those are positive actually. Okay. So, for example, if n equal to 1, we have only one pole. So, you can use k equal to 1 here, okay, and then this will give in this formula where sin pi is 0. So, we are left out, and cos pi is minus actually minus 1. So, we are left out with s equal to minus omega 0. So, that is just one thing, and we are ready with direct application equal to k equal to 1 actually, it will give us that. Okay, what about little more? Okay, suppose you have like second order thing actually, how do you do that? This is for the first order system, what about second order system? So, let n equal to 2 in that case. Okay. So, first is like cos theta plus j sin theta to the power m is nothing but cos m theta plus j sin m theta actually. Okay. So, if you put n equal to 2 here, okay, this is n plus 1 is 2 plus 1 3 divided by 2 into 2, which is 4. So, that the fraction is 3 by 4 actually. Okay. So, n plus 1 divided by 2n is 3 by 4. So, you have a formula like this, and this is direct substitution of this formula whatever you have. Okay, I mean this complex exponential we expand it in terms of cos and sin basically, that is all we are doing there actually. Okay. So, case 1 is okay, so we put to start with k equal to 0. So, in this formula, okay, whatever formula we have, we start with k equal to 0, and then S1 turns out to be like that, which is somewhere here actually. Okay. And obviously, this location is left hand side of the this S plane. So, we will buy it, we will tell okay, it is right, we can accept actually. right. So, this particular length omega 0 will dictate, that will design, I mean we will select omega 0 and then tell okay this is good or bad, that is again dependent on several factors like your for example, your jumping ratio or omega, I mean what is that, the sigma part real part of it, the percentage overshoot, like that actually. Okay. So, these are this will give us S1 which we are ready to buy. Okay. Now, when you put k equal to 1, because k equal 0 is that, now next we put k equal to 1, this will give a pole location which is actually in the right hand side. So, obviously it is destabilizing. So, we do not want I mean obviously we do not want to take that actually. So, this one we are accepting, this one we are rejecting actually. Okay. Now, the next one k equal to 2 is again it will pop up in the fourth quadrant and then it is rejection also. K equal to I mean k equal to 3, it is in the third quadrant which is again positive, I mean this is stabilizing. Okay. So, anything that is second quadrant and third quadrant we are going to buy. So, this is going to be third quadrant. So, we accept it actually. So, if you see this line starts from here and nicely takes some sort of a clockwise revolution actually. Okay. So, this attempts to kind of distribute the poles in a fairly kind of good manner basically. Okay. This is because the arm length remains same, it is just a rotation which happens. So, it tries to place the poles in a good way rather actually. Okay. So, this is what is Butterworth polynomial is all about. If in a higher order case you can also keep on doing that, okay. You can change your omega 0 and then again excite this one more time and things like that actually. Okay. So, these are just guidelines by the way, I mean these are not, certainly these are not design procedures, these are simply guidelines to start with actually in a way. All right. So, let us try to take a little time to apply all this to a example, like this example I taken from Ogata again. So, we are talking about an inverted pendulum, okay, on a card sort of thing, and then the dynamic equation derivation and all we are not interested that much. What you are telling is okay, that part is done already and this linearization and other things have already been done. So, we have a linearized system equation that way about the inverted position basically. So, we want to stabilize the ball, I mean the inverted pendulum in its vertical equilibrium, vertical top actually. Okay, so, that is what we want to do. It is obviously a unstable equilibrium point, you want to stabilize that using control system actually. Okay. So, if you see this and remember these y1 and y2, we are taking x1 and x3 only. Okay. And it is also, so this x1, x2, x3, x4 is just not the pendulum, it is also the movement of the cart. Okay. So, cart is moving and that is where your control input is acting. So, by moving the cart back, I mean forward and backward in an appropriate manner, can you stabilize the pendulum on the vertical equilibrium position, that is the problem actually. So, the movement, the control conditions are all related to not only this pendulum swing, but also the cart movement actually. So, these are all coupled systems that way. Okay. So, what you are measuring here is x1 and x3, which is like position measurements only. X1 is probably this theta and x3 is this position movement of the cart actually. Okay. So, that one we are not that much interested here, because we are not designing an observer for this. I mean that is probably next class we will see observer design and all. So, this equation is not that relevant as of now, but here we see okay, this is our system matrix A matrix, this is our B matrix, this is our C matrix, D is 0 obviously. Okay. So, and then just to work with some numbers, we select these numbers appropriately obviously. So, these numbers A, B and C will have numerical values now. Okay. So, first thing is to check controllability, design step 1. Okay. So, we form a controllability matrix, it turns out to be like that, and then determinant is not equal to 0 and hence rank is 4, which is a full rank matrix, and hence the system is controllable, and that is the reason why there is hope we can actually attempt to design a control system. Okay. So, let us go to the step 2. Okay. This is what we are talking about a practical example of using our theory what you know. So, Si minus A is nothing but the open loop characteristic polynomial. A matrix is like that, okay. A matrix is given like that. So, Si minus A turns out to be like that, okay. And Si minus A determinant turns out to be just these two terms, okay, s to the power 4th and s square. So, we want to write it in general S4, SQ, S square, all sort of things, and then equate the coefficients properly actually. Okay, A1, A2, A3, A4. Okay, so obviously A3 and A4 are 0, 0. A2, A1 is nothing but this cube is not there in this polynomial. So, A1 is 0, and A2 is S square is nothing but minus 20. 0.601. Okay. And normally the highest power coefficient is always 1, we do not require that actually. Okay. So, we have collected these coefficients A1, A2, A3, A4. This exercise gives us that actually. Okay. And by the way, in general, all this determinant evaluation can easily be done by using symbolic software, if it is too much I mean high dimension and all that, that is not a problem. Okay. Now, find the transformation, that is what you are interested in, right. We are interested in applying method 2 here, okay, the Bhaskara thing. So, T is nothing but m times W, where m is already known to us, m we have already evaluated, okay, that serves a dual purpose by the way. So, serves the controllability check as well as we will use it in the T matrix actually. So, m times W, where W is like this, that is the form. So, that is well, that is again a small mistake probably, this is equal to that obviously, okay, right. W just substitute the coefficients A1, A2, A3 and you will get that one actually, okay. So, that is equal to that actually, okay. So, now we can see that T equal to mW and we can very easily compute, W is already there, m is also there, okay. So, m times W we multiply and we get that. Once T is there, T inverse can be computed, okay. That is how it is. And then we can find, we are not yet done because we have simply computed T and T inverse yet. We have to find this, we have to also cater for this desired closed loop poles and all, and desired closed loop poles are given like that. Also remember, for real characteristic equations are typically real polynomials. So, the closed loop pole locations, the only restriction that to select is they have to be complex conjugate. If they are complex number, they have to, the conjugate pair it should exist actually, okay. So, these two are real number, double pole at -10, that is okay, or these two are complex conjugates of each other. So, that is the restriction how you want to select actually, okay. By the way, Butterworth polynomial naturally gives you that, because whatever you saw in the second quadrant and third quadrant naturally gives you that actually. Anyway, so it happens like this, mu1, mu2, mu3, mu4 that way. So, the desired characteristic polynomial happens to be like this, okay, all these 4 multiplications, and you expand all that, and then it will give us the coefficients alpha 1, alpha 2, alpha 3, alpha 4 that way. Once you expand, the good thing about complex conjugate polynomial is once you multiply them together, the resulting polynomial is real actually, okay. So, these two together will give us this real polynomial and these two together will give us that polynomial actually, okay. So, again you multiply and then collect these coefficients alpha 1 to alpha 4 actually. So, that is what we do here. So, then find the state feedback gain matrix which is directly available. This is the row vector times T inverse. T inverse we have already computed, this row is available now, okay. So, just compute it and then u equal to minus kx, this is what it is actually, okay. So, this is all about some example and all that with single input system. Now, what do you do when the system is actually multi input system, okay. So, in general u is this, u is Rm, and the problem here is this does not admit kind of a unique solution. Pole placement technique is good only for single input systems in a very good way basically, but there are techniques, tricks and techniques to handle this issue to a limited extent actually, okay. So, what I told here, that is the same thing written here, the gain matrix is not unique, okay, even for fixed closed loop poles actually, okay. It is essentially the gain matrix is not unique, that is all actually, okay. Okay. Then the matrix, the mathematics becomes kind of involved, but it is traceable, it is not becomes a kind of untraceable mathematics. I mean, they are all linear systems, that is why they are kind of popular actually. Okay. So, it is traceable mathematics, but it becomes little more involved and hence it is not that good actually. Okay. Oh, again there is a small mistake again. Okay, this is certainly u. Okay. So, x dot equal to x plus bu and u equal to minus kx. Okay. Okay. So, the gain matrix is like that in general. Now, the gain matrix is not a row matrix, I mean not a row vector, but it is a matrix in general actually. Okay. In that sense, what you want to do actually. Okay. So, one idea is you can eliminate the need of measuring certain states by purposefully selecting some sort of a combination actually. Okay. Appropriately choosing the closed loop poles actually. Okay. For example, if your control formula in a symbolic sense is like this, okay, where mu1 and mu2 are pole locations, okay, then purposefully I will select one mu2 equal to beta, okay, so that this term equals to 0, and hence I do not need to use x2, I can eliminate sensor actually. But this is all subject to the condition that beta is actually good, beta is in the negative side and all that, negative side of the S plane basically. But if it happens that way, some polynomial, some coefficient, this one need not be mu1, it can be anything actually, but just a function of x1, and this one, okay, right, I mean this one needs to be certainly mu2 minus beta, okay, this need not be mu1 actually, it can be anything, that is okay. Okay. But this is of importance, this has to be like that, okay. Then certainly I can select mu2 equal to beta, right, provided beta is negative, that is the only condition actually. Okay. Then the beauty of it is I do not need to measure x2 anymore, so I can eliminate a sensor actually. Okay. But again you have to see whether that is the design is good only with x1 information, this will excite this output feedback control sort of ideas basically. Okay. Okay. Then the second thing is, okay, can you relate the gain matrix to proper physical quantities, that means suppose you have ux and uy, now ux which is like let us say position sort of ideas, or ux is related to object x primarily, uy is related to object y primarily, they are coupled, the x and y systems are coupled obviously, but you want to preserve that independent feedback sort of ideas. Okay. So, the plant 1 will act on measurements from plant 1, and plant B controller will act on measurements from plant B itself. The information exchange from plant A and plant B, even though they are weakly coupled, those need not be considered actually. Sometimes these power plants operating at different locations, power system control and all in electrical engineering, these kind of ideas are useful actually. Okay. So, then you talk about okay, these elements are purposefully enforced to be 0. So, your entire freedom of 8 entries have reduced into 4 entries actually. Okay. So, these are some of the ideas you can invoke for even better simplicity, but these are more or less heuristics actually, they are more or less kind of intuitive, but it is not mathematically rigorous actually. Okay. So, if you want to have mathematical rigorous thing, then there are techniques available, which is one of that is eigenstructure assignment control, where we are not interested in only eigenvalue placement, but we will also interested in eigenvector directions, they have certain meaning and all that. So, we are not going to discuss that particular thing here, but another alternative thing is we can introduce the idea of optimality, okay, which will lead us to optimal control design for linear systems, especially stabilizing controller design will fall in the framework of linear quadratic regulator, that we are going to talk here actually. Okay. So, that is, and you can also visualize that optimal control or the LQR controller is kind of an eigenstructure assignment controller. Okay. Ultimately, it will give us a formula for which it is valid for multi input system and all that, in general it is valid. So, implicitly it is doing some sort of a eigenvector shaping, but we are not enforcing that to begin with. Okay. We will enforce it indirectly sort of thing actually. Okay. So, these are some of the tricks and ideas that you can follow. Another idea that is I have taken from the website, which is a very good company of course, dealing with control system estimation and all that actually, they have put that idea in a very neat way. So, this is like okay, may not be able to read here. So, let me explain this concept in a little detailed way sort of thing. So, what you are telling here is like you have this number of inputs. Okay. So, you have this entire pole placement technique given in this diagram sort of thing. So, either you have a single control variable or you have a multiple control variable. Single control variable, nothing too much to worry about actually, things are in order. When you have a multiple control variable, all that you are doing is you can define some sort of a linear combination of those variables. Okay. Suppose you have let us say u1 and u2, then you talk about a vector v which is like partly u1, okay, let us say mu times u, okay, mu is not a good variable probably because that is already taken. Okay. Let us say eta times u1 plus 1 minus eta times u2, okay, where eta is a number between 0 and 1 actually. Okay. That means you are formulating some sort of a convex combination of u1 and u2, you are actually kind of distributing the load in a percentage sense. Let us say 1 eta is 0.3, then it is 30% U1 and 70% U2, like that actually. Okay. So, you do that, and then because you are reducing this way, you are not sure whatever B matrix pops up with V. So, ultimately you started with x dot equal to Ax plus Bu. Okay. So, this will, we are interested in writing Ax plus some sort of a B bar times V. Okay. So, the system was certainly controllable with respect to A B pair. We are not sure whether it is controllable with respect to A and B bar pair. Okay. So, that we need to kind of do that actually. So, we want to verify whether A and B bar, this pair is controllable or not actually. Okay. Now, once this satisfies this, then you can transfer the system to a controllable. I mean, what essentially it tells is, you can, once this condition is satisfied, you design a V actually. Okay. Once you design a V, then again you distribute that in terms of U1 and U2. That means, in this particular case, eta times kind of I mean, you can this right. Okay. Once you design this V, you know what you are doing actually. That means, this V consists of let us say 30% U1, 70% U2 actually, right. So, you can kind of try to redistribute back and tell, okay, this V I will kind of partition that and tell, okay, 30% load will be taken by U1 and 70% will be taken by U2. I mean, that is the idea there. Not a very neat approach, but certainly it does work in many cases, especially for linear systems. This, because of the superposition principle, comes to your rescue. So, that way it becomes helpful in this particular thing. Okay, but this method is need not necessarily guaranteed to work. It also, suppose you select a different eta, it may be controllable suddenly. Okay, for a different eta, it may not be controllable, like that actually. So, you have to do some iterative design for making it work actually, this particular approach. Okay. But then I mean, for single input systems, it is certainly a definite good tool. What we talk actually, this pole placement design. So, in summary, what we are telling here is, in this particular class, we talked about pole placement control design for single input system in a good way. Multiple input systems, you can do, you need, I mean, you can do a job, but it is not very straightforward exercise because of non uniqueness of the solution. Okay, but forgetting that effect, there are ways to handle that. Okay, there are I mean, may not be very mathematically rigorous way, but there are ways to handle that. But if you want to be mathematically rigorous, then you have to use this either eigenstructure assignment or some sort of optimal control LQR thing actually. Okay. But other than that, we discussed about like method 1, 2, 3. How do we make use of these ideas of stabilizing, I mean, stabilization and all that, to come up with a controller design, and primarily we focused on state feedback controller, okay, of the form of U equal to minus kx. Okay. So, entire thing was boiled down to how do you design a K matrix or properly basically. So, for that we discussed about 3 methods, and all these 3 methods we also demonstrated, I mean, one of the methods we demonstrated using this inverted pendulum, and then we will continue further with our discussion on like how to make use of that these concepts that we discussed here for observer design next class actually. Okay, with that I will stop probably. Thank you.